Good afternoon, good morning, good evening, everyone. Glad to see you here. If you're tuned into the audience, we've got a special treat for you today. We're going to be working our way through some live content, and you should be able to actually work through it with me. So that should be pretty fun. Let's see if we can make that work. Pardon me. Still getting over the very last bit of a cold, but I'm almost done with it, which I'm very grateful for. Let's see, I'm going to share this screen. And let's go and take a look at the news this week. So remember, as always, you can go to Cilium.io newsletter. This is where we aggregate all of the news coming up. Most recent release was July 2nd. One of my fellow EBs, Shedrack, has been on a tear with Cilium case studies this year, with over 20 published and a few more on the way. Cilium is well on its way to have the third most case studies, but just behind Kubernetes and Prometheus. In the past weeks, there have been from DigitalOcean, Nameling.com, PostFinance, SysReady, and WSO2, which is pretty awesome. That's four continents, and four completely different industries. We also have a really interesting article in the technical about reverse engineering eBPF programs. So if that's something you're interested in, definitely check that out. In this year's BPF conference at the Linux conference, there was a modernizing BPF for the next 10 years talk, which is pretty interesting, including an insight into the possibility of compiling the entire Linux kernel in BPF ISA, which is pretty wild. And there's going to be a bunch more talks in that series, so definitely check those out if you're interested. Aradan has made some Cilium labs with Kind. Don't know why you need that, but that's interesting. Oh, Docker installation. Got it. So saying you brought up just a regular old machine. This is actually pretty interesting. The way I have always done this, I'm a big fan of this one, is I think it's get.docker.io, which is a script that does all of the steps that this does, but automatically with some detection for the different distribution that you might be running. So that's actually pretty neat. Get.docker.io. I would recommend that over this, because this gets a little pretty complex, and get.docker.io kind of just handles it all for you. In the Kind installation, download the binary, the Cilium tool, and away you go. Even has a BGP lab, has a mesh lab. That's pretty cool. Nice. Very, very cool. Ransomware detection using machine learning with eBPF for Linux. Dust is a PWRU to trace IO request. Wow, that's pretty cool. So PWRU, for those uninitiated, is packet where are you? And what this does is it allows us to trace a packet through like all the different layers that packet might pass, including any eBPF steps. And apparently Dust is like the mechanism for a trace request. It's kind of wild. Or on the IO side, I guess. In the ecosystem, case study with DigitalOcean. eBPF enabling security and performance to coexist. Lots of really great stuff happening there. Nico's networking book is now available in Chinese. This is built enterprise dashboards for Cilium, operating at scale, agent errors, rate limiting, map pressure. Pretty good stuff. Just last week, I was actually at Security Day, which is a security based conference up in Seattle. That was a really great conference. Had a wonderful time presenting there, both with my co-presenter, Mr. Kyle Quest of the Docker Slim effort, and also presenting the talk that I'm about to give here with you. So lots of really great stuff. We'll say hello to the chat. Hello, good to see you. How's it going? Welcome, welcome. Yeah, get.docker.com is pretty neat. Yeah, definitely save some time if you're just trying to do a quick install for something. No. All right. Well, let's get started here. So what we're going to do for this lab or for this session is we're going to actually explore a full like interactive lab. And if you would like to participate with me, then what you can do is you can go to iso.go.2/sailing echo. I'm going to put that link in the chat so that you should be able to see it there. If you navigate to that, that will take you to this page, and you'll be asked for your information. This is just to make sure that there's no bots like trying to DOS the service that we're using. So if you just provide your information, then we can get started, and this will bring you to this page. Hopefully everybody in the audience can see it, but if you can't see it, I'm actually just going to put it up on a big screen here. So .io. Note. Skip. It always forgets I like them key bindings. Okay. So go.2/sailing. So that is where we're going. ISO go.2/sailing echo. No space, no dash. ISO go.2/sailing echo. And when you navigate there, you might have to provide some information. But soon enough, you'll see this screen. So I'm going to go ahead and press start, and we're going to talk a little bit about what this is going to be. So this is going to be the lab that I presented at Cloud Native Security Con just last week. This will take up pretty much our hour. As you're watching, you're going to see that down here on the right, it's loading up the lab. So it's not actually ready to start yet. So it'll take about a minute, maybe 2 minutes for it to get started. Won't take too long. While we're waiting, you can actually shift through with your arrow keys or with this little arrow here and see what we're going to be doing. A little bit more about the components that we're going to use inside the lab, including this graphic, which highlights basically how Tetragon can be used, right? Like lots of different things that Tetragon itself can do. This lab is specifically about Tetragon, and we're going to use this lab to actually explore a couple of really interesting parts. We're going to use it to explore the recent XZ vulnerability, and we're also going to use it to explore the writing policy that would limit applications within a specific Kubernetes namespace to only access specific IP addresses. So in a way, we're going to use Tetragon to enforce network policy as well, which is pretty wild. Now, I've done this lab, so I have this restore progress section. You probably won't have that. It'll just say Tetragon docs and repo. And if we check these out, I just want to make sure people were aware of this. If you go to tetragon.io, there's tons of content on Tetragon, including how to get involved, some Tetragon policy library stuff, the code of conduct, how to install Tetragon, and a bunch of other great information about Tetragon itself. So if you want to get involved, if you want to come help us tell a story, if you want to check it out, definitely go to tetragon.io and you will be able to see it there. That's why the first part of the lab was showing off that part of it. The next section, we're going to actually go ahead and install Tetragon into a cluster that we have running. So we would kick over to terminal 1. We could actually run the command with kubectl get nodes. We can see that we have a single node here. And we're going to go ahead and run the install command to install Tetragon into that node. And the next thing we'll do is we'll just make sure that it actually does get completely rolled out. There should only be just the one pod here because it is just a single node cluster. Tetragon does operate as a daemon set, so it would actually normally put one node on every, there we go. Yeah, it's a little better. Yeah. It'll put one pod on every node. And you can think of Tetragon as basically a framework that would allow for us to compile eBPF programs against literally anything in the Linux kernel. And this gives us the ability to distribute the work of compiling those programs to each pod running on each node inside of your environment. Now, another important thing to know about Tetragon is that Tetragon does not need Kubernetes to operate. It can actually operate entirely on its own on a Linux server. So everything that we're going to explore today, you could actually do without having any Kubernetes at all. You can actually just run this directly on a server. There's no requirement that Kubernetes is involved, which I think is pretty darn cool. Once you have installed the Tetragon agent, we're going to go ahead and continue. And in this first section, what we're going to do is we're going to actually make the qubit that is running our Kubernetes cluster, our kind cluster here, we're going to make it vulnerable to the XZ SSH attack. And once we've done that, we're going to show how Tetragon can be used to determine that a vulnerable version of the XZ library is being used by SSH, which is pretty cool. So let's go ahead and get started there. In terminal 1, we're going to exec into our kind control plane node. And that's because our kind control plane node is actually running as a Docker container, which is, I know, a little confusing, but what this means is that kind stands for Kubernetes in Docker, and it basically creates a systemd enabled Docker container running itself and all of the components that are presented on that underlying image. So if you do Docker, if you do systemctl list inside of that kind control plane node, you're going to be able to see that systemd is running, that all the other things are running. You'll be able to see all the containers that are running, et cetera, et cetera. So for this lab, we're going to make this running kind control plane container vulnerable to the SSH attack. So let's go ahead and step through this process. The first part of the process is that we're going to pull down a vulnerable version of the liblzma library. That's liblzma 561-1, and that is a known vulnerable version of the liblzma library that we're going to use to exploit our SSH command. The next thing we're going to do is we're going to install it. Now that we've downloaded it, let's go ahead and grab it. And then, of course, we're also going to need SSH. So we're going to install and enable SSH as well. Now we have SSH running. We need to go ahead and copy our keys into the Docker container. And what that allows us to do is now we can actually SSH in, right? So in this next section, we're going to explore security observability events from the vulnerable dependencies that we have actually just installed on this underlying control plane node. So now that we have a vulnerable version, let's go ahead and set up Tetragon to alert when vulnerable software is loaded. We know from the blog post, and if you're curious about that blog post, you can actually click right over here on the right. Oh, and apparently, did I break that? Oh, I did. Wow. Okay. Sorry about that. Never mind. Whoops. But the blog post can be found if you go to isovalent.com/blog. And then inside of here, you search for XC. You're going to find that blog post. And this is the blog post I was referring to. I'm not sure why the embedded link isn't working, but this blog post really gets into all the details around it. And this, I mean, ironically, there's just been announced, like in the last week, another vulnerability called regression, which again can be detected by understanding what libraries are being loaded by SSH, right? So this same example of leveraging the liblzma library, or determining that the liblzma library is being loaded, actually translates directly to being able to identify those servers that are being used, that are loading vulnerable software in the regression um, CVE that just came out. That's pretty cool. So we got our SSH up. We have copied our keys over. The next thing we're going to do is we're going to actually load a tracing policy. And before we do that, let's click over to the editor and click on the tracing policy that we're going to load. So in this tracing policy, what we're doing is we're loading the security memory map file that is being used by SSH. So we're basically, you can think of it a little bit like an LDD, right? Like when we're doing a library load, for when the SSH binary starts up, we're going to look at the things that SSH binary is loading from disk, as far as like the dependencies that it's loading. And if we see one, we're actually going to post. We're going to make some noise. We're going to say, hey, this SSH binary loaded up this vulnerable version of code. So let's try this out. I'll show you how this works. So back in Terminal 1, let's go ahead and apply the XC/SSH YAML. And then we're going to jump into the Tetragon container, and we're going to start watching for events. Now, the neat thing about Tetragon is that by default, if you're not filtering those events for specific types of events, you're going to see every event that happens on the underlying host. And so this actually indicates some of the information that we're able to see happening at the underlying host. And we can see what type of permissions a thing has. We can see what the actual arguments are. We can see a lot of really great contextual information about what's happening on all of our hosts. In this particular case, this kind cluster is actually only running one kubelet, right? It's only one node. So we're not seeing a ton of information, but we are seeing all of the changes to the kube proxy configuration, which is pretty wild. Remember that when you make any change to kube proxy, that change represents a complete reload of all of the things in IP tables. IP tables isn't atomic. So when you see an IP tables command like this, that change is actually going to represent a complete reload of all of the rules in your IP table set. So lots of interesting stuff happening here. Now, we have gone ahead and we've started our event stream. Let's kick over to Terminal 2. We're going to get the IP address of our node, which in this case is 172.18.02. And then we're going to try to SSH in and just run the date command. So let's go ahead and do that. And we'll say yes, because we trust the fingerprint. It's just a container running on the local host. And now if we kick back over to Terminal 1, here in just a second, it does take a second if there's a lot of events that are not being filtered, we should be able to see the memmap being loaded up, and it will alert us that a vulnerable version of software was loaded by the SSH daemon. Give that a second to load up here. I passed it, have I? Nope. Nope, not yet. Let's just rerun the command real quick. Here we are. I just found it here. So the process, SSHD, running inside of the kind control plane node, is running as capsysadmin. It got started up by somebody running SSH 172.18.01 date 18.0.2.date, and then the command was date. when the process started up, we saw that it loaded the vulnerable version of libLZMA. And then the process exited because the command was done, and we moved on with our time. That's pretty cool. Now, let's jump into the next section here, where we're going to explore actually using tracing policy to limit access to specific networks. Check. Now, this is actually introducing a relatively new function inside of Tetragon, where we can actually write where we can write tracing policy and have it only affect those containers running in specific Kubernetes namespaces, or we can have that tracing policy affect only containers with a specific name, etc. Right, which is actually really cool. First, let's go ahead and jump over to the relevant Tetragon docs and just take a look at the docs real quick. So the motivation here is Tetragon is configuring tracing policies. Broadly speaking, tracing policies define what situation Tetragon should react to and how. The what can be, for example, specific system calls, or in our example, the loading of a specific library. And the how defines what action Tetragon agent should perform when a specified situation occurs. The most common action is generating an event, like a post, but there are others: returning an error, executing a function, killing the corresponding process. Here we discuss how to apply tracing policies only on a subset of processes or pods running on a system via the following mechanism: Kubernetes namespace policies, pod label filters, and container field filters. Tetragon implements these mechanisms in kernel via eBPF, and this is important for both observability and enforcement use cases. Prior to this change, when you would write a tracing policy, it would affect everything in the entire cluster, right? There was no limiting the effect. So if you wrote a policy that said, anytime anything makes a setUID system call, I want to be informed, then you would receive that information about any process, whether running on the underlying host or inside of a container. But what if you decided to kill any process running setUID because you feel like that's a risky system call? So as part of your security posture, you might decide, I don't want anything to run a setUID system call anywhere in the system. And so you enforce that policy, and now it's actually not even allowing containers to start up because setUID system call is required for container startup. And you're like, dang it, well, what if I could actually write that same policy but have it be namespaced such that it would only affect containers and not the actual underlying host. So the container could start, but inside of the container, it would not allow the setUID system call. Could I do that? And this is where namespace filtering comes in. And there's great examples of trying this out on your own if you don't want to use the lab. But there's some pretty cool stuff here about how it all works. So in our case, let's go ahead and get started. Let's jump back into Terminal 1, and we're going to go ahead and run this next command. And this will create like an echo server. And the point of this is to basically go ahead and create something in the cluster that we're going to allow to communicate back and forth. Because the policy that we're going to enforce in this particular case is this RFC 1918 CIDRs policy, where basically, because this is a namespace policy, and we're not actually trying to match on any specific type of container, this means it will match on every container running inside of the namespace that I apply the policy to, and it's going to watch for a kprobe with TCP connect. And when it sees that, it's going to look at the argument for that TCP connect. And if that argument is not in the destination address of 10,000 or 10. The RFC 1918 networks here, then I want to kill it, right? So that means that what we should see is if I were to try and use curl or ping or any of those two, actually, I guess ping wouldn't work because that's ICMP. But if we were to use curl to connect to like www.google.com, that should fail because Google.com, I promise, is not one of these RFC 1918 addresses. These RFC 1918 addresses are meant for local use within your intranet, not within the internet or the external use. However, that echo service that we created will fall inside of this category. And we're going to kind of explore that and see how all that works. So back in Terminal 1, we had gone ahead and deployed the echo service. Let's go ahead and deploy a NetShoot container. NetShoot is a pretty cool container image. It's used a lot in troubleshooting or diagnosing particular different problems that people run into. And what this does is it has tools like curl and ping and NSLOOKUP and all of those things. So in our example, let's go ahead and try to do a curl to the echo service. We can see that it works great. Right? We're able to connect directly. Now we haven't applied any policy. So if we were to try and also curl Google.com, that should also work, right? Because there's currently no limitation. So let's go ahead and lock down those CIDRs. So we'll exit out of our exec container here, and we should see root add server now. So the next thing we're going to do is we're going to apply that policy that we created, and you can see that it says tracing policy namespace. And because I haven't specified a namespace, it will apply to the default namespace where all of our pods are running. So once you've done that, let's go ahead and start our trace. We're going to watch for events using Tetragon. And this time I'm actually going to be filtering the events to only those events that are relevant to the default Kubernetes namespace. Okay, so in Terminal 2, let's jump into our container and try to do a curl. Oh, sorry. That's the typo. I got to fix that in the lab. :8080. And we should be able to see that get containered or get connected, right? You can see right here in the curl command, I actually added :8080 because that's the port the service is listing on. So again, I'm able to see that I'm able to connect, and that's great. We go back to Terminal 1, we can see the connection. Oh, you can see the SIGINT because that was where I hit Control-C because I'm going to the wrong port. But now I'm able to see the connection. Everything is great. Back to Terminal 2. What if we tried to connect to Google.com? We can see that Google.com lands in the 172.253 namespace. Let's try to curl it. Right? We did actually see that when we did the curl, the command was terminated with the exit code 137. And when we looked up the IP address, we can still look up the IP address. It's got an IPv4 and an IPv6 address, both of which are outside of our range. So here we see the connect to 64.233.167.101, port 80. And there we see the SIG kill. And if we want to do this again to say like Microsoft.com, let's try Microsoft.com. Microsoft.com. What do you think will happen? Terminated, exit code 137. Hop back over here on this side. And because of our filtering, we can see right away it tried to connect to 20.112.250.133, which was Microsoft.com, and it got killed. That is pretty cool. So the next thing we're going to do, let's just go ahead and take a deeper look at some of the events that are happening. Because while these one-line events are useful, they're actually hiding a lot of really valuable context behind them. So the next thing we're going to do is we're going to jump back over. We're going to hit Control-C. And then we're going to go ahead and install a couple packages into our Tetragon container. And now we're going to jump back over to Terminal 2, and we're going to run that same command against, say, Microsoft. We got terminated, and we can see the signal was SID-kill. We can see the parent process, the name of, we can see the actual integer associated with every namespace running against this particular process. We can see what relevant capabilities the process had. We can see what the actual command was. We can see a ton of information here, and it's all in structured JSON data. So when we're looking for like relevant security events that are actually useful to help us understand what's happening inside of this environment, this is where we can actually get a lot of that data, right? So tons and tons of information in structured JSON data that can be used to derive real insight about what's happening inside of your infrastructure. Now, one of the questions that you might be asking is, like, did we just apply network policy without applying network policy? Like, why didn't we use network policy for this? And I mean, kind of, yeah, right? This policy will affect network traffic, but it's likely better to use something like Cilium network policy to handle this. But what if you're not running Cilium? What if this was just Tetragon installed on a server? Might you want to write network policy on that server to limit access to it, to limit access to things outside, to limit access to things within your infrastructure that you don't want it to have access to? Tetragon can run standalone on a host with no Cilium and no Kubernetes and no Docker installed. So we have described how the namespace effect works. We've described this whole example. Let's go ahead and do our check. Oh, no tracing policy deployed. I thought I fixed that bug. Well, let me know if you see that. You don't think you should, but if you do, then we'll fix it. So the next thing we can do is we're going to use Tetragon to detect a container escape. Now, before I get any further than this, I do want to point out that all of the lab stuff that I'm actually showing you is something that we host on isovalent.com. So if you go to isovalent.com/labs and you wanted to just play with different features or functionality of Tetragon or Cilium, or the different ways that we can actually leverage this stuff, definitely come check out the lab and try it out, right? So there's tons of great labs here, including things like getting started with eBPF, getting started with Tetragon, the advanced use cases, et cetera, et cetera. And a lot of these badges actually include a badge. So if you do make it through the lab, you can actually get a badge that you can put up on your own social media, with anything from LinkedIn to X, etc. I do recommend starting with the Discovery Labs, as they're a great way of understanding like what labs we think would be most useful for you. So if you are curious about how to get started here, I definitely recommend getting started with the Discovery Labs. All right, back to our lab here. Now, what we're going to do here is we're actually going to do a little bit of an exploit on the underlying host. We have a little bit of privilege to do so, but we're gonna kind of play with like how all of this would work in just a standard Kubernetes environment. So the easiest way to perform a container escape is to spin up a pod with privileged access in the pod spec. Kubernetes allows this by default, and the privilege flag grants the container all Linux capabilities and access to all host namespaces. The host PID and host network flags run the container in the host PID and the networking namespaces respectively, so it can interact directly with all processes and network resources on the node. So in terminal 1, we're gonna go ahead and start a filter for a tetragon, watching for our pod, the Sith infiltrator. Now, anytime there's a pod that gets created, anything that pod happens inside of that pod, we're going to be able to see an event right here in this side. So let's go ahead and terminal 2 and create that guy. If we pop back over to terminal 1, we should see the pod creation steps. So these are all the steps it took to actually create this particular pod. And if we run kubectl get pods, we should be able to see it running. And there it is, the Sith infiltrator. So in terminal 1, we're going to go ahead and identify the container start. Well, following process exec and process exits. Right. So this is the actual startup of the pod, the Nginx pod process starting up, and then there's some template stuff that the M stub actually running, which is all part of the Docker entry point shell script. And you can see the default configuration edits for the Nginx daemon. There is the substitution of particular components inside of there. We're changing the listen, we're turning daemon off, etc. Now, let's actually add a tracing policy that will observe privilege escalation. This is going to observe it in any namespace. This isn't just the default namespace, this is any namespace that we'd be able to detect it. And in terminal 2, let's go ahead and do some insidious things, right? So I'm jumping in to the Sith infiltrator pod. And once I'm there, I'm going to use the nsenter command to basically move into all of the namespaces associated with PID1. So this is a little bit like SSHing in as root. Now, because I've moved into all of the namespaces of PID1, that means I can actually see everything on the underlying host just as though I had SSHed in as root. Will we be able to see that there was a change in namespace for a given process? Will we be able to detect that? And the answer is yes, right? There's the set ns command we were watching for, and we saw the change, right? The process we were got moved into a completely different C group, IPC, UTC, net, PID, mount, and time namespace. And that is how we detected that that happened. And then the bash command started up. Now that we're running the bash command as root on host, the next thing we'll do is we'll establish a foothold on the node and hide any trace of our activity. Now, the way we're going to do this is we're going to actually use a feature of Kubernetes to actually hide an underlying pod. But before we do that, let's go ahead and add a tracing policy in terminal 2 to be able to detect the creation of an invisible pod. We will need to apply a third tracing policy. This tracing policy will be used to monitor read and write access to sensitive files. In our case, we're going to observe the x64 syswrite and x64 sysread system calls, which are executed on the files under the etc Kubernetes manifest directory. In terminal 2, let's apply the policy. And if you want to look at the policy, you can either cat it or vi it, whatever you want to do. But let's just take a look at it real quick. So what we're watching for is we're actually going to apply this to a specific pod. We're watching for the security file permission. This is called false. We're going to watch for the file and the integer, whether it can be written or read or written. And then we're actually watching for a prefix of the arguments to be etc Kubernetes manifests. So let's go ahead and run that command. I think we've already applied it. Yep, there it is. Okay, and the next one we're going to do is we're going to create the invisible pod. So for that, we're going to jump back into terminal 1. We're going to run this command, which will exec us into the Sith infiltrator. Actually, we're going to watch for events for the Sith infiltrator. Back in terminal 2, and jump into the Sith infiltrator. We're going to escalate our privilege all the way to root. We're going to cd into the Kubernetes manifest directory, and we can see the etcd control plane, the API server, the controller manager, the scheduler running here. Let's go ahead and create another pod. And you'll notice that right up here under metadata, we have the name hack latest, and we have a namespace called doesn't exist. That will be important in a second. So let's validate that that container did in fact get created. If we do CRI kettle PS, we can see hack latest running right up here. So it is in fact working. We do see it get created. But are we able to detect that it exists inside of Kubernetes, right? So we jump over to terminal 3, and we run kubectl get pods all namespaces. Where is hack latest? It's not here. And if we go back to terminal 1, will we be able to see the event of it getting created, right? And so we did see a write to the etc Kubernetes manifest hacklatest.yaml. So we were able to detect that it happened. Now that we actually persisted the breakout by spinning up an invisible container, we can download and execute a malicious script in memory that never touches disk. So let's click on next to see how to do and detect that. So to execute a malicious Python script in memory, what we're going to do, we're going to jump into terminal 1 here. We're going to start looking at our events. In terminal 3, let's enter the Sith infiltrator pod. Let's again escalate our privilege. Find the container ID of the hack latest container, right? So we're going to use CRI kettle PS to look for hack latest. We're going to grab the ID of the container, which is this one here. And now we're going to exec into it. In the logs in terminal 1, we should be able to see the process exec. In terminal 2, to be able to fine-grain the security observability events for Cilium Tetragon, start monitoring the events that match process names curl or Python in terminal 2. So let's pop that open. And we're watching for any process. We're looking at all of the events in the compact form, and we're watching for any event that has a process curl or Python associated with it. Back to terminal 3, and we'll go ahead and run our in-memory piece, right? So I'm actually pulling down a Python script called zipper.py, and I'm piping it directly to Python. So the next thing we're going to do is we're going to look at the kind control Python security event. So let's jump back over to terminal 2. And here in a second, we should actually see the match. There it is. So we see the curl command, and we see the Python process start up, and we see that Python process is running. You can also identify the sensitive socket connection opened via kernel as in our case, we see this connection. I don't think we've actually installed the network piece, so it's probably not going to show up for us. So while the following process exec events show the malicious Python script execution in memory is finished with execute 0, which means it was successful. So you can see the payload working. Well, now that we have definitely proven that this is an attackable thing, what can we do to secure it? What can we do to enforce policy, right? What are ways that we can actually use to limit this access? So let's explore a few rules. So for file monitoring enforcement, one of the things we could do in this scenario, we really started getting into trouble when the attacker managed to write the hack.latest in .yaml into the etc Kubernetes manifest directory. Right? And so if we take a look at the editor, and we look at etc Kubernetes manifests, you can see this, again, this policy here is actually just doing this is just how we notified ourselves that this happened. So the next thing we want to do is we actually want to stop it from happening. So we're going to put the next section here right at the same layer as match args. Right? So there's our match args. We're going to create a new action, and we're going to add the action override and the arg error -1. So now when there is a match arg, when this arg actually matches, we're also going to give it an action and tell it, I want you to stop it. I want you to kill it. So this will not allow it. And there are other options, right? There's a signal, there's get URL, you could actually apply a function, you could do a sig kill, lots of different ways to do this. We see the change was saved. Let's jump back into terminal 1 here, and we'll apply the new one. And if we didn't mess up the YAML, then it will apply correctly. And in the next section, let's go ahead and jump into terminal 1 here. Let's run this command. We're going to be watching for events on the pod sys infiltrator. In terminal 2, we're going to run the bin bash command. We're going to exec into the root namespaces. And then let's see what happens when we try to run this command. Operation not permitted. If we go back to terminal 1, we can see that right there, that sig kill. Return with status 2. This enforcement is applied directly in the kernel without any action from the user space program, as eBPF program generated by Tetragon is self-sufficient to both monitor and enforce. So when we see it, we enforce it. It doesn't have to go back to user space or anything else like that, which is pretty darn cool. Similar rules can be written to block the binary execution by command name to avoid the curl command, for example, or to prevent the original NS escape that allowed access to the host namespace, etc. So I think that wraps up our whole lab for the day. I hope that some of you were able to go along with me on this. This was a really interesting experiment. I hope that you found this useful. I really like the way we built our labs. I feel like it's actually super educational, and I think they've done a pretty good job of actually, keeping them relevant, keeping them updated. And big shout out to the labs team for making all of this possible. So I hope you enjoyed it. Again, if you have tuned into this episode after the lab is no longer available, you can actually explore any of the other labs available at isurveillance.com/labs. So remember, all of these labs are available to you. You can just jump into any of these and explore them. They're a bunch of fun. Thank you. Glad to hear you liked it. So all these labs are available. Definitely go check them out. There's so many more things to learn about the way Cilium works, the way migrating from Flannel works, the way Cilium IPv6 networking and observability. There's just a ton of really great content on there. And that's all I had to share with you today. So I hope that you all have the best weekend of your lives, and I will see you in the future. So thank you so much, and I'll see you next time.